So someone asked on um, my most recent video why, well, let me just show you their actual comment. Still can't quite wrap my head around smoothness. Is this somehow related to smooth maps between manifolds? Why is the open stabilizer criterion the right one? Great question. I'm going to like it and give it a heart. In fact, I think this is such a great question that I asked it myself almost 3 years ago on Math Stack Exchange. So I'm gonna put the link of this and some of the other links from this video uh so you can see it yourself. I had the same question. I feel like I still don't have the right answer. So like let me just first say, in some sense, yes. Um, I mean, right? The thing is, somehow, you know, like if I'm studying a Lie group like GLNR, right? Um, and I want to study representation, well, this is a smooth manifold and this is a smooth manifold. Well, actually, we have to be careful. If V is finite dimensional, this is a smooth manifold. If it's not finite dimensional, I'll say something about that in a moment. Um, but in the case where it's a finite dimensional representation, then these are both Lie groups. And so yeah, you want, in order for this to be a meaningful map, you want to simultaneously preserve the group structure and the smooth manifold structure, right? So of course, when you have this other kind of analytic thing in here, what you would like to do is also have this be, I mean, at the very least, you would want it to be continuous, right? Because like what do p-adic derivatives mean? Okay, there's like theory behind that, but then like, it's one thing to talk about like functions from QP to QP or something, right? But then the thing is we have QP to C, and these are like very incompatible topologies. So, uh, so what do we do, right? Um, I mean, the answer is we have this open stabilizer condition, but like maybe that's not very satisfying, right? So I asked this question because I expected there to be some nice conceptual answer, right? Like you try and prove um write down the definition of continuity and maybe this falls out. And well, there's a nice little comment here. And then Paul Garrett, who, if you don't know, he's a famous uh mathematician doing like automorphic forms Langlands type stuff. And he also has a lot of great notes. He's actually kind of like if you know Keith Conrad's notes in algebraic number theory, he's kind of like the Keith Conrad of like automorphic form stuff. So he has a lot of great like one-off PDFs. Anyways, so I'll leave the link so you can read this yourself. But he more or less uh outlines like what happened originally, and it was kind of just sort of the right thing, sort of guess that came out. And he mentions, I think this is an interesting point, although I still would like to understand this stuff better myself. He says that there's these rationalizations or explanations, which are sort of like post hoc, right? Where you can talk about, functions factoring through locally finite limits and profinite groups and stuff. But that's not originally what inspired people to come up with this definition, right? Now, regardless, I still like to see those things that sort of, even if it's a post hoc rationalization, I still like those post hoc rationalizations, right? But like, it's also kind of a good point that it's like, well, that's not how we got there, and then that's kind of weird, right? Um, and so there's some explanation here, but I don't know. It's somehow like mysterious to me, I would say. So a couple of things. There's another Stack Exchange question where someone asked this. I'll also link it. Around not much after I asked my question. Um, and yeah, there's some comments, there's some discussion in the comments from Keith Conrad. Did I say Keith Conrad? Brian Conrad's oh no, yes, Keith Conrad. Yeah, the one with all the notes. Yeah, so there's some nice discussion back and forth here. They get into a little bit. Here's something I've heard before. I've heard an explanation in terms of Schwartz-Bruja functions, right? So at least for functions, I haven't gone through this argument myself, so it's not so clear to me that this falls out. But like, so Schwartz-Bruja functions kind of make sense in the real case as something like we're studying. And then, you want to do Fourier theory and you'd like some sort of space of L2 functions that's closed under the Fourier transform and has nice properties. And you get this theorem that's the Schwartz-Bruja functions, right? So I've heard it said, like I've heard people say that you can explain as a post hoc realization that these locally constant is like the right definition of smooth, because if you look at measurable, you look at measurable functions on the p-adics, you look at the ones that are L2, and then you define the Fourier transform, and then you want a space that's closed under the Fourier transform, and like the smoothness condition kind of falls out of that. But I haven't gone through this derivation myself, so like I'm passing on hearsay to you, right? There could be an understanding there. Um, yeah, so that's basically all I can really tell you about it. The one other thing I did want to mention, this set of notes, I realized it doesn't answer the question that I really want, or that you want, but there's a nice set of notes by Fiona Murnaghan, representations of locally compact groups. So like this is pretty general. And over on page 31, there's a discussion about the reason I'm bringing that up is because the infinite dimensional case. And the reason I'm bringing this up is, yeah, so you when you want to consider continuity in the infinite dimensional case. So this is relevant even for Lie groups, and for even for p-adic groups. But like for p-adic groups, the maps are actually technically they're continuous with respect to the discrete topology on the complex numbers, which fine, I guess. So a short and perhaps unenlightening interlude of a video, just to say I don't know. And hopefully someone else uh will see this and can maybe um uh offer a compelling explanation. Because I still don't, I feel like I have one myself.